My name is Bence Gerber. I'm a product manager at ANSYS. This video will show a demonstration of product life simulation. Durability is an increasingly important factor in product design. All products exposed to repeated cyclic forces are subject to failure from fatigue. Examples of these products are vehicles such as cars, trucks, buses, trains, airplanes, heavy-duty machinery such as farm equipment, tractors, rigs, generators, wind turbines, gas turbines, and even some consumer products. Historically, we have over-designed products to avoid failure. To be competitive in today's environment, however, there is a need to make informed decisions and take into account the potential of fatigue failure. We have to know what are the variables in a design that have the greatest influence on durability. Understanding how dimensions, shape, materials used, and other variables influence the life of a product is best done with simulation. It is the most cost-effective and efficient way to gain insight into the causes of failure. ANSYS nCode DesignLife provides a comprehensive fatigue process that can capture complex loading conditions and simulate the life of a product, identifying when failure will occur and which part will fail first. Once the process has been simulated with DesignLife, the product can be optimized for the desirable life that needs to be achieved. The following demonstration shows the simulation of a trailer hitch under repeated loadings. The steps taken to set up and run the problem and the process of optimization within the ANSYS Workbench environment will be shown. The demo is done by Hari Subramaniam, a technical services engineer at ANSYS Inc.
So this is the model that I'm going to do a demo on. This is a trailer coupling, and this end of the trailer coupling goes into the back of a car or any automobile. So what I'm going to do is I'm going to apply some force on this ball, and we're going to do a static structural analysis. Then take those structural results into ANSYS nCode DesignLife and do a fatigue analysis and calculate the life of this part. But the ultimate aim of this demo is going to be how to create parameters, whether it's a CAD parameter or a simulation parameter or a DesignLife parameter, then optimize this design so that we can increase the life of this part. So at the end of the demo, the workflow should look something similar to this one. So I will have some parameters coming from my CAD, some parameters coming from my static structural, and some parameters coming from my DesignLife encode. Then using the parameter set, I'm going to do a goal-driven optimization, and my goal is to increase the life of this part. So to save some time, I have already solved my static structural. So I have my geometry and I have solved my static structural. I will show you what I have in my static structural. So this is the model, and I have applied a fixed boundary condition on the side walls. I have applied a force on this ball. Then I ran a simple linear static analysis. Let me animate this deformation result. So the force is stretching the trailer coupling. Also, I can look at my equivalent stresses here. So the maximum stresses develops around this neck region over there, and also the stresses develops near the fillet region over here, and the top and bottom of the fillets, and also some stresses are developing in the elbow region also. So the material that I used is AISI 4340. This is actually coming from my nCode material library. This nCode material library can be accessed from your engineering data. Let me show you where that one is. So in the engineering data, when you go into the engineering data sources or the library, there should be a library for nCode material library. So within that material library, you will have all the nCode material library, which basically has two sets of material properties, one set for your strain life and the other set for your stress life. And to add any material to your model, you would just click on this plus symbol over here, like the one that you do in a normal static structural analysis. Okay. So I have my material defined and I ran my static structural. Now I'm going to do the nCode DesignLife fatigue analysis. So all the modules that are available will be on your left-hand side. So in any normal analysis, you would do the same thing. You would just drag and drop the analysis to start it. So in this case, it actually has EN stands for strain life and SN stands for stress life. Basically, it has 3 of EN, 3 of SN, constant amplitude where your cyclic loading is of constant amplitude, in time series where you have a time history, whether the time history is coming from your experimental data or your test tracks, and also you can do a time step. So this repeats the same thing for your stress life also. In addition to that one, you also have SN vibration, which you can use for your nCode vibration fatigue, random vibration fatigue. So in this demo, what I'm going to do is I'm going to do a stress life analysis using the time series. So I'm just going to drag it and drop it onto my static structural. I'm going to drag it and drop it to the solution of my static structural. So my solution gets transferred to the nCode DesignLife, and also the engineering data will get automatically transferred. Now let's go ahead and open up the DesignLife. For the users who has never seen nCode DesignLife graphical interface, it looks very similar to a Workbench interface. So it has these blocks. These blocks are called as glyphs, and all the available glyphs will be on your right-hand side over here. You could see there is a group for input glyphs, function glyphs. There are glyphs for display, and there are glyphs for DesignLife. So if you want to add any of these glyphs, it's similar to any Workbench products. You would just drag and drop it into this workspace. In this case, we have pre-built the modules for you, so you don't have to drag and drop the necessary glyphs. Most of the glyphs are already available or pre-built for you. So each of these glyphs will have input pads. These color-coded ones are called as input pads, and the left-hand side are input pads, and the right-hand side are the output pads, and the data flows from left to right, from the input to the output. So in this case, what we're going to do is we're going to do a stress life analysis, and it has actually 3 input pads. The first one is the simulation input that is coming from my ANSYS static structural results, and I have a time series input that is my time history, which is coming from my experimental data, and also there is a bill of material input that is the material mapping. So these are the 3 input glyphs that is going to come into my stress life analysis. Now I can even display my simulation output, which is the input for my stress life analysis. So that's my simulation output. On any of these glyphs, when you do a right click, there'll be an option called properties, and that will have all the default settings that's currently being applied to this glyph. If you want to change it, you can change it from that properties. So in this case, let's go to the properties. I can even display my FEA results within nCode DesignLife. I can select what the result case that I want to plot. In this case, I just have only one load case, so I have only one result case, and I can plot what type of stresses that I want to plot. I can select either from von Mises to all other principal stresses. So in this case, I'm going to plot von Mises stress. So I selected the von Mises stress. I'm going to give an OK, and it will automatically plot the von Mises stress. I can also maximize this by clicking this button over here, and let me put it in an isometric view. This is the same contour plot that we saw in my FEA ANSYS mechanical. So let's minimize that one. Let's go to the time series input. Currently, I don't have any time series input right now, so I'm going to go ahead and add it. Again, it's the same thing. You would go and do a right click, go to the properties, add data. In this case, I'm going to browse for my load files. I'm going to give a scan it. Then that is the load file that I'm looking for. It comes in an extension S3T. If you have any load case files in a text file or a WordPad file, you can change it using this ASCII translate on your left-hand side. You can use that one to translate those files into an S3T format, which can be read into nCode. Okay, so that's the file that I want to use. Actually, this is called as Carlos TC test. It stands for Car Loading Standard Trailer Coupling Analysis. So I'm going to add that test to my time series input, and I can display my time series input. So in this case, it is a time history that is taken from my experimental data. Also, what I can do is I can also do a rainflow cycle counting of these input. So to do that, I'm going to go to the basic TSP. I'm going to select a glib, which is appropriately named as rainflow cycle counting. So I would just drag and drop the glib over here, or I can actually drag and drop it to this input pad, output pad of the time series that will automatically connect it to my rainflow cycle counting. So rainflow cycle counting is a means of taking a variable amplitude, stress or strain histories, and from it identifying a number of cycles with different range and mean values. So also I can say, okay, I want to display the rainflow counting values in a histogram. So to do that, I would just go to the display glibs and I would select histogram. In this case, it's the same thing. I would just drag it and drop it to the rainflow glib. So that will go ahead and plot the histogram graph of this rainflow cycle counting. Let me move these things a little away here. Okay. So I have my simulation input ready, time series input ready. Now let's go ahead and into the stress life analysis and set all other parameters now. So I'm going to go one by one. So first one that I'm going to do is edit material mapping. I want to see what material I'm using for it. So this is a single part, so I should have just one material. So I'm going to go into that material. So that is 4340. Let's see what are the material properties that it has. So it has the elastic modulus and all other material properties required for my fatigue life analysis. So in this case, when I go to my graph, actually this one has more than one SN curve. It actually has 3 SN curves based on R ratios or stress ratios. As we know that the mean stress affects the fatigue life, and it is reflected in shifting of the SN curves are up or down. The tensile mean stress, like the green one, usually decreases the fatigue life, and the compressive mean stress, like the red one over here, actually increases the stress life. So either I can have inputs where I have different SN curves for different R ratios, but if you have just one curve, I can select the mean correction, stress correction criteria, which I'll show you in a minute. So let's go ahead and close this material properties. Now let's go back to the stress life analysis. Let's take a look at the load mapping. So I'm going to do select edit load mapping. So in the edit load mapping table, so that is, I have only one load case that is coming from my FEA static structural results. But when you see this time series, actually it has 3 inputs. It has forces in X, Y, and Z. But in the simulation, I just have only one input, that is my force in X direction. So it actually selected the correct file for this case. If it is the forces in X direction. But if it chosen the wrong one, I can uncheck this auto configure and change it by dragging and drop it. Let's say this is the wrong one. I want to select FY force. I would just drag it and drop it over here. So it changes to FY. In this case, actually, I want to apply FX. So I'm just going to drag it and drop the FX here. Also, I can set up scale factor or offset to this. If you want to set up a scale factor, you can just type in that number of scale factor in that table over there. Now let's give an OK to the load mapping. Let's go back to the stress life analysis. So we are done with material mapping, load mapping, and I'm going to go to the advanced edit. In the advanced edit, it will have all the default settings for this stress life analysis. Let's go to the advanced editing. Now it has all the default settings for all different things. What I'm looking for is the SN engine. That's what I want to look for. So in this case, it lists all the settings that I've currently chosen for this analysis. I'm going to point out a couple of ones. Mean stress correction. So in this case, it chose interpolate because we have, as I showed you earlier, my material property actually has 3 SN curves. So I can just interpolate the values based on those 3 SN curves. But if I just have only one SN curve, I can either choose a Goodman theory or Gerber theory based upon what I want to choose, or even I have the option to select none. So in this case, interpolate is the right one to choose. So I'm just going to leave it that one. And also in the combination method, the current method that's being selected is absolute maximum principle. Also, I have an option to select either von Mises or sine von Mises stress. Sine von Mises stress takes the sign of the largest absolute principal stress. It basically helps you to identify compressive mean stresses because several of the mean stress theories treat positive and negative mean stresses differently. So you can select those options over here. All other options, I'm just going to go with the default. I'm going to give an OK to this. Now my simulation is almost ready to run. I can hit this play button over here to run it. But my ultimate aim for this analysis is actually do a design optimization on my fatigue life. So I'm going to set those parameters also in here. So to do that, I'm going to go to this DesignLife clip over here, and I'm going to select a clip called Design Explorer Output. So I'm going to do a same thing, drag and drop it over here, or I can just drag it and drop it to this output pad of the stress life analysis. And that one will automatically create a Design Explorer Output clip for me. Let's do a right click again, go to the properties and see what are the properties it has. So it has the option, either you want to parameterize your life, damage, safety factor, or scale factor. In this case, I'm going to parameterize my life. So I'm going to select life. And also, since it's just single part, I don't want to have results for different materials. All I want is a single parameter for my model. So I'm just going to select false for my parameter per group. And parameter type that I want to pass it to the Design Explorer is going to be the life. And I'm going to give an OK. In addition to the output that you can set, ANSYS DesignLife also gives you some parameters that you can parameterize for as an input parameters. So to do that, what you can do is you would do a right click on the stress life analysis, go into and select Edit Expose Properties. Let's go ahead and select that one. So in this Edit Expose Properties, let me maximize the screen over here. It gives you a couple of options. One is certainty of survival. I can just click here to parameterize that. And also it gives you another option called scale factor, which I can also parameterize that. The scale factor actually applies a scale factor to the stresses before the fatigue calculations. And the certainty of survival allows statistical variations in the material behavior to be taken into account. The usual application of this is to provide a more conservative prediction to ensure a safer design. So these are some of the input parameters that I can set. So now pretty much I'm done. So I have my simulation input, time series input. I have set my input and output parameters that I want to look. I can hit this play button over here to run the simulation, or I can actually go into the project page and hit update project over here. That will also solve my nCode DesignLife. So you can look at the progress either in this progress toolbar, or I can just go to the nCode DesignLife and look at the progress bar. So when it has a like a red button over here, so that means it is solving or computing in that particular clip. So now you can see that the analysis is almost done. It is trying to capture the contour plots, the table values, and also detailed summary as a report. And also it passes the variable to my Design Explorer output. So it's going to take another less than a minute to solve it. Okay. So once everything is done, everything will turn into white button. So this one will all turn into white. So now everything is done. So I have my contour plots displayed over here. Let's maximize this one and let's take a look at the results what we have now. So I'm going to maximize this one. Let me put it in an ISO view. So the maximum damage actually occurs at this neck radius over here. And also it occurs in this top and bottom fillets and also somewhere in this elbow region also. So right now the contour plot is the damage plot. The other properties that I can plot are, again, going back to the properties. In the result type, I can select either life or even I can plot maximum and minimum stress that it saw during the time history. So let's take a look at the life of this part. So I'm going to select life and I'm going to give an OK here. So that's going to update my life of that part. So it shows that this part can be subjected to almost like 10,000 cycles of that time history. It's slightly smaller because we use a scale factor of 10. And also, it calculates something called as hotspot reductions. Hotspot reductions actually goes over this contour plots of these results and lists the critical region it actually does not list the top 10 critical region or like top 10 damage region. It mostly, it is almost like displaying the top 10 localized damage regions. So actually I can click on this button over here and look at those top localized damaged regions. So it actually lists my node numbers and the other material IDs. So let's go ahead and look each one of them. So I can click that this node over here, and it will show me where that node is in this contour plot. So that's where the neck radius is, and I can click here. That's my fillet radius, and that's on this elbow over here, and the other one is on my fillet down. And in addition to this one, it also gives me the damage, the non-proportionality, maximum stress and minimum stress of these nodes and the life of these. Let's close that one. So in addition to these contour plots and hotspot detections, it also displays all the results in a table form. When you maximize this table, it actually lists the results for all of these nodes. So it usually lists in the order of, in the ascending order of the life. It repeats. In addition to the life, it also displays what stresses it saw, and also what kind of calculation method it used. In most of these nodes, you can see that normal method has been used, and some of the nodes you would see it also used critical plane method also. Okay. So in addition to these tables, it also creates a report for you. You can actually save this report. It lists the load histories, it lists the contour plots, it lists the bill of materials, and the last page lists all the fatigue results. Okay. So now let's go back to my Workbench project page, and let's take a look at all these parameters. So it basically created a parameter set coming from my CAD static structural. In addition to that one, it also created a parameter set coming from my nCode DesignLife. Now let's go ahead and open up this parameter set over here. So it has some input parameters that is coming from the geometry, which I will talk about it in another couple of minutes. So these are the input parameters that is coming from my SN time series, so certainty of survival and the scale factor, and the output parameter from my DesignLife is going to be the life I'm going to look at. So if you want to set up a what-if study, you can just pretty much enter those different design points and hit update all design points, and you can look at the design points. But the objective of this demo is to do a design exploration and look at optimizing the design life. Now let me return to the project here. So the parameter set is ready. Now what I can do is I can drag and drop my goal-driven optimization into this parameter set to do the goal-driven optimization. So I'm going to drag it and drop it to the parameter set that will link up this parameter set over here. So now I can go in, do the design of experiments, create the DOE matrix, solve it, then do a response surface, then specify the goal for the optimization and select the best candidates from the response surface. To save some time, I have already solved a design of experiments and response surface. The only thing I have not solved is optimization, which I will show you in a minute. Okay. First, let's go into the design of experiments and see what we have there. So we have some input parameters that is coming from my geometry, and I did not specify any input parameters from DesignLife encode for this one. So all my input parameters is coming from my geometry. Let me quickly show you what are the input parameters. So basically, I have 5 input parameters coming from my geometry. One is ball diameter, the neck radius, the shank length, the fillet radius, and the sidewall thickness. So these are the 5 input parameters that is going to come into my Design Explorer. Let's go back to my Workbench. So you can specify lower and upper bound for each of these parameters to create the DOE matrix. By default, ANSYS creates plus or minus 10 from your initial value. So based on these 5 parameters, ANSYS created somewhere around 27 design points for this based on the default method called central composite design. It basically chooses the corner points and then some midpoints and also some points in the center. So once it created this DOE matrix, I can hit update design of experiments. That will go in and solve each one of these design points. And in this one also, I can display graphs of each individual input or output parameter based on each of these design points. So in this case, I can plot how my maximum stresses changes based on these design points also. One thing that I forgot to mention is, as an output parameter, I have DesignLife from my nCode DesignLife. Also, I have parameters from my static structural where I'm looking at the weight of the part and also the maximum stress of the part. Now let's return to the project here. Now go to the response surface. So in the response surface, I'm going to go with the default one, which is a standard response surface, full second order polynomial. It mainly uses for each output variable, it creates a function of input variables, and the function is a second order polynomial. Since we are doing some kind of a curve fitting or surface fitting, it is appropriate to look at the goodness of the fit. The coefficient of determination will give you how good the input parameters are captured in the variability of the input parameters is captured. The best value is 1, and it will be listing for each output parameter. So in this case, the weight of the part and the equivalent stress has almost 1, and the life is 0.99. That's pretty good. And you can look from this graph from the observed design points and predicted design points. It's a pretty good fit over here. And in addition to that, also I can look at the response as a 2D or a 3D curve. In this case, I'm looking at my life as a relationship to my neck radius. Also, what I can do is I can change it to a 3D graph, and I can look at 2 input parameters and how those 2 input parameters changes my life. So in this case, what I'm looking at is I'm still looking at my fatigue life, but I'm looking at 2 input parameters. One is neck radius and ball diameter, and I can pretty much change any of those from these XY axis. And also it gives you spider, where you have these slider where you can change these values and see how your output parameters varies based upon the response surface that you have right now. So I can change these values and see how these output parameters vary. Okay. Now let's go back, return to the project. Now let's go into the optimization. So in the optimization, I have to specify what is my objective for this optimization study. So my objective is, so it lists all my input parameters and my output parameters. So I'm going to specify the objective on my output parameters. My main objective is to maximize the life of this part. So I'm going to maximize the life. And also, definitely, I want to minimize the stresses of the part and also minimize the weight of the part. Since some of these objectives are contradicting, maybe the weight of the part and the equivalent stress is contradicting each other, because you're saying minimize the weight of the part at the same time you're saying minimize the stress of the part. So you have, it's also good to specify which is important. So in this case, I want to give higher importance to my fatigue life, and I want to give a little lower importance to my stress and my mass or the weight of the part. So once this one is set, I can hit update optimization. This is actually the basic default method is screening method, as I'm showing you on the screen. It actually screens the response surface. It samples how many number of points. In this case, it's 1,000 points, and it will sort out those 1,000 points based on the optimization criteria. Definitely, you can increase these number of samples that's being generated. So once the optimization study is done, it will list the top 3 candidates based upon your optimization criteria. So in this case, the higher the number of stars, the better the design is. In this case, it listed candidate A, B, and C. And in addition to this one, it also lists something called a sensitivity chart, which you can take a look at it. So the sensitivity chart actually lists for each of these output parameters. So I have an output parameter for my weight, stress, and my life. I can look how the input parameters affects my output parameter. So basically, it is sensitivity going from +1 to -1. Let's take a look at the sidewall thickness over here. So the sidewall thickness actually is a positive sensitivity to my weight of the part, meaning if I increase the sidewall thickness, then the weight of the part increases. Okay, that makes sense. Now let's take a look at the output parameter for the sidewall thickness. It has almost negligible influence on my stress life and maximum stress, and also on my life. So if my objective is not to change anything, not to affect my fatigue life, but I want to reduce my weight of the part, so I can vary this one to reduce the weight of my part without changing either my stresses or my life. Let's take a look at one more variable. the neck radius over here. So the neck radius has a positive influence on my life, meaning if I increase my the radius of my neck, then the life is also going to increase, and it also has a negative influence on my stress maximum, meaning when I increase my neck radius, my stresses are going to go down. So these are the couple of options that you can take a look at. The other one is the trade-off charts that you can take a look at. Once you're done with the optimization study, one final thing that you should do is, again, this is actually a predicted value based on the response surface. This is not a calculated value. So the one final step you should do is do a right click on the candidate, whichever candidate that is appropriate for you. Do a right click and do insert as verification point or insert by a design point update, where it will insert this particular point with these input parameters as a design point and solve it once, and you can compare it to the predicted and the calculated value. If your response surface has a good fit, these two values should be very close. So now I have completed my goal-driven optimization study. So hopefully it's pretty easy to use, coming from DesignLife all the way to the goal-driven optimization.
For more information, please refer to our web pages, www.ansys.com, our list of products in structural mechanics, and specifically the ANSYS nCode DesignLife page. You might also find useful information by searching our web pages for DesignLife. Thank you very much for your attention.